Okay, let's start off with a geometric sequence that starts off similarly to the other one, but obviously takes a different path. Okay, so this is starting to talk about geometric. Oh, can't spell today. Geometric sequences. Okay, so let's say I start with the same problem. I do 7 push-ups, and then the next day I aim to double it. Okay, so then there's going to be 14, right? Then there's going to be 28. You get the picture for that one. Okay, so what is that going to look like? Let's see what that looks like with an explicit definition. So again, I'm multiplying by 2 each time. Okay, an explicit definition for that one is going to be a sub n is equal to 7 times 2 to the n minus 1. And you'll be able to do these later in the course. Okay, so let's just check that it generates it. A1 would be 7 times, I plug in 1 for the n, 1 minus 1, so it's just going to be 7, and then it's going to be times 2 to the 0. And so I really do get 7 out as my first term. Okay, and if I'm finding A2, it's going to be 7 times 2. Okay, and in this case I'm going to want to plug in n minus 1, so it's going to be like 2 minus 1. Okay, so that's going to be 7 times 2 to the 1, which, sorry, my A2 is 14. You can kind of see how that's working, that this definition gets me to what I need. Okay, so that would be an explicit definition for this series or sequence. And a recursive one would look as follows. Okay, I would start with A1 equals 7, and then I want to define things in terms of the previous thing. So A sub n is going to be 2 times A sub n minus 1. Okay, so in other words, I give a start off, and then I tell like each one, how do I generate the next one from that. Okay, so let's do one more geometric sequence. Let's see if this makes sense to you guys. Okay, so let's say I had 0.4, okay, and then 0.04, 0.004. Is this geometric? It is. I'm multiplying by 1/10 each time, okay? And again, one way that you can check that you really do have a geometric sequence is you're going to find what's called the common ratio. Okay, the common ratio, what you want to do is you want to take a term over the term before it and see that it has the same ratio. Okay, so the term, this term divided by the term before it, and if I do that, I see the ratio of that is 1/10. The top is 1/10 the bottom. Okay, so as long as you get that same ratio, you need to take later term divided by the one previous term before it, and you need to do that. You could check that twice to make sure that you're always getting that same ratio. Then it's going to be geometric. Okay, so that's really the check for if it's geometric. Okay, so we've gone over several things so far. Okay, so let's just kind of summarize here. So an arithmetic sequence, it's going to have a common difference. So you're always going to be adding something every time. Okay, so an arithmetic sequence, you're always adding, it always has D, which is a common difference. And you find that for each sequence. Okay, so for an arithmetic sequence, let me make one extra tie-in, okay? An arithmetic sequence is going to go very nicely with a line. The problem with it is, remember I told you on day 1, I did like 7 push-ups, day 2, I did 10. Let's see, day 3, what was it, 13. Day 4, it was 16. You could see that it's going to have like a slope of 3 simply because every day I go over a day, I add 3. I go over a day, I add 3. I go over a day, I add 3. Okay, so it is going to hit at this intercept, and it's going to be like what I'll kind of call a ghost term, because it's going to hit like at 0, 4, if you think about it. And so if I kind of go back, I know on the first day of quarantine I did 7, but you could kind of go backwards one day and say, what would be the 0 day? And the 0 day, you know, would it have existed, I would have done 4 push-ups, if that makes sense, even though I really started the sequence here. So anyway, you kind of have to go backwards by a term often to get that 0 term to really see the intercept. But the main point is that you can see that like a line is going to be what's going to underlie an arithmetic sequence. And hopefully that makes perfect sense, because what you're doing, you're always going over the same amount. You're always going over 1 to advance your sequence, and you're going up by the same common difference every time, which is going to be your slope. Okay, so we talked about that. Let's go with geometric sequences and build a connection there. Okay, so geometric, okay, you give obviously a start value, and then you're continually multiplying by the same kind of number all the time. Okay, so let's see how that's going to work. Okay, so for this one I did, I'm going to actually do it a little, well, I guess I can do it the same way we did it before. Let's do it the same way. A sub n is 7 times 2 to the n minus 1. Okay, so graphing this one, it's a little bit hard to see, but hopefully you can see like, oh yeah, it kind of looks like a little bit like what you'd expect for an exponential equation. So what I have to do here, I can plug in 1 easily, right? If I plug in 1, I get just 7, right? Okay, so like if you think about it, I'm actually going to get 7 halves as my intercept, because, you know, if every time it multiplies by 2, then you could think, well, what did the sort of ghost thing have to be before to make the whole sequence work? If it would have been 7 halves of a push-up on the 0 day, which would have been really weird. But anyway, you can kind of see, obviously, you don't really want to go in the negative terms, but if you want to just kind of see what functions underlying that, it would be an exponential function. So here you have like 0, you know, 7 halves, and then you have 1, 7. That's when the sequence really starts, is the 1, 7, okay? And then we had 2, 14. Obviously, this grows really quickly, right? And then what the next day was 3. It's already up to 28. So obviously, I'm not really doing this exactly to scale. But the important thing is, like, hopefully you can make the connection that with the geometric function, geometric sequence, an exponential function is going to kind of underlie those points. Obviously, the sequence is only dots of points, but if you were to kind of draw something continuous that would connect through all those points, it would be an exponential function that would fit those points. Okay, so let's take 2 real world examples that are kind of like that. Let's say that you're given $500, okay, on your first birthday, okay? So we'll make that A1, okay? And then let's say you're given $100 for every birthday after that, and you want to keep track of the value in the account, okay? So one way I could do that is with let me do a recursive formula for that. I think that makes more sense. So let's do either one works though. Okay, so $100 is added to what's already there. So I have to start it off, and then $100. Okay, so let's go ahead and calculate for this situation what A2 would be, okay? Obviously you know what it would be, but A2, using the formula, would be 100 plus A1, right? So if n is 2, then A sub n minus 1 would be A1. Okay, so of course I can plug that in because that's my start value, okay? So that's 500. So then obviously I get A2 equals 600. Obviously it's hard, I mean, it's tedious to use this formula generating mechanism, but I just want you to understand like how that works for another example, like how you can use some different formulas in order to calculate different things that you need to calculate for those things. Okay, all right, so let's do one more example like that. Let's say that instead of that, we're gonna put just that, let's say that you only got $500 for your first birthday and then you didn't get anything else after that. Now, the first case, let's say it wasn't put in an interest-bearing account or anything like that. You just stuffed it under the mattress or whatever. But let's say in this case, it makes sense. You're like, oh, well, maybe what I should do actually is put it in an interest-bearing account. That would make more sense. So let's build that up. What would that look like? Okay, so let's say what happens in this situation. Let's say it's a really modest interest rate. So it's only 3% per year, okay? So I could multiply what's in the account, okay, by 1.03, and I'm going to get what would be the next year's value for that money. So I put $500 in, I multiply by 1.03. Hopefully you understand that what that would do is generate, you know, it'd keep the $500, but also generate an additional 3% interest, and then each year it'd be multiplied by 1.03. So that's like compound interest like we've seen it before, but just compounded annually for that situation. Okay, so that would generate, hopefully you could see that what I'm doing is I'm doing 500, okay, this is a little harder for me to do in my head, but 500 times 1.03, you get the next value, and then times 1.03 again, you get the next value. You kind of see like what's happening, that you can see that it's a geometric sequence. Obviously, in this case, it'd be kind of nice to have a calculator to work that one through, but you can see that's continually multiplying by the same number. So that's going to be geometric. So that's another example of a geometric. Obviously, the one up here where I just stuffed it under the mattress, and like each year, let's say your grandma gave you $100 and you stuffed it under the mattress or whatever, put in a box, whatever, you know, it's adding $100 every year. Okay, so in that case, it's going to be an arithmetic sequence. So those are two more examples that you might see in an everyday life situation.